Hello, everybody. I'm really thankful to be invited here by the organizers to tell you a little bit about the perspective of all of that we discussed today, and beyond that of the large space integrator, so critical industry, let's say. Sorry. Something popped up. Okay. I'm representing Airbus. Airbus in UK, that is kind of competence center in Europe for critical planetary mobility missions. And I'm representing obviously a huge team of people who are contributing to those projects. Those projects are not done by single person. So my presentation will be about the SFR mission that, as you already know from this session, got cancelled last year, yes, or early this year, sorry. But the activities we describing here, and I'm using as an example, were finished at the end of the last year with the field trials. So sample fetch rover mission was part of Mars sample return. And the whole purpose of the rover was to bring the samples from the depot, so from the place where the Perseverance supposed to drop them, collect them, bring them on board, and bring them back to the rocket for a liftoff. Pretty simple, right? I mean, well, navigation from point A to point B, and some pickup. Yeah. Our customer, we need to thank our customer ESA for excellent collaboration and kind of inspiring all those efforts and specific developments, ambitious developments in this project. And I will use the same slide also to introduce you to Shabli. Shabli is the breadboard platform that is kind of flight representative to the flight rover of the point of the mission where we've been developing those field trials. We've been attending those field trials. Is it? Do I have laser point? Okay. It is four-wheeled rover with compliant wheels of NASA design, with 4 steerable axes. Sensor suite includes navigation cameras on the PTU, so on pan tilt unit on the mast, and localization cameras down here at the level of the bathtub, what we call. Obviously, we also have onboard IMU, but that's basically it, what we have available. And obviously, talking as an industry, it would be, I mean, I cannot skip speaking about requirements and about kind of scope, detailed scope of the mission. We're talking here about the rover that is safety critical, mission critical, and it's actually not only mission critical for itself, for the science of the rover, it is mission critical for the huge effort of bringing samples back to Earth. So the rover safety is a priority. Then we're talking here about 300 to 400 meters per sol, which was super ambitious for the time of those field trials, and it still is on the edge of what is possible with those systems. We're talking here about, as David mentioned before, we're talking here about the speeds of the rovers of 1 to maybe 10 centimeters per second per minute. Centimeters per second. Yes, sorry. So pretty slow, unimaginably slow for the Earth applications, obviously. And additionally, inside depot, we need to do really specific, really accurate positioning and really accurate following of the paths to the particular sample tubes to pick them up, which is another phase of the mission that is on top of the traverse, the next challenging bit. And I will just skim through general constraints. Whoa. Okay, you see everything already? Good. I can skip that. I will just skim through general constraints that are kind of obvious for space missions. But in our case, in case of those missions, we're bringing them to the extreme. So we're talking here about available sensors. I already mentioned 2 stereo cams and IMU. Okay, that's relatively fine for the navigation for the traverse. Bandwidth, minimization of the bandwidth to the extreme. We have only limited windows. We have only limited bandwidth. We have only limited time for communication. We want to avoid anything related to that, at least for the traverse phase and pickup of sample tubes. Then power budgets and processing power are highly related. We have really particular trajectories. We have processing power of 100 to 250 megahertz single core for doing all the mission. So I'm not sure if people those days can even imagine those. I mean, it was some time ago we had those in our PCs. It can be even compared to the calculator. Calculator is faster those days. Then obviously industrial heritage and maturity. This is something that normally in research or in let's say early phase companies, it's not really important, but for those missions to deliver such a mission within, let's say, less than 10 years, this is super important. And you will learn on the next slides why. Mission operation concept you already know. Quick introduction. I mean, you have the details you can read in the paper that was published last year. But the quick introduction to the overall architecture of the rover GNC. I'm from GNC, so the presentation is a little bit focused on GNC, obviously. Quickly going through, we have localization. Well, first we have navigation management module that basically deals with the navigation of the rover in terms of high-level choose of navigation mode. Is the terrain easy? Which mode we should go? Is the terrain hard? We should go to the full autonomy stack. And also it's kind of state machine complexity. So there's no magic, there's no AI. Then we have localization module, which is basically relative localization using visual odometry, IMU, and sound sensing to give you relative pose change. And then you have absolute localization that basically gives you a reset of the accumulated error over time. It's based on the matching of orbital data with locally perceived perceptions. Then all of that is used for navigation. We have stereo pair processing, modeling, terrain evaluation, and map generation, typical grid cost map, which is used for path planning. Then any plan is put to the trajectory control. Trajectory control executes those paths with 20 centimeter accuracy. It doesn't matter what kind of terrain we traverse. And that's it. I mean, there's extra module for this particular project, hazard prevention, that basically deals with the relaxation of several aspects of the autonomous navigation to speed up the traverse where the terrain is really, really easy, which is 70% of the case, and some monitoring to keep rover even more safe. Okay, and this is why the things are complex and costly. So the validation process. I mean, we've seen a lot of companies, small companies promising rovers, etc., postponing them because of that. Like validation cost of the mission design and bringing concept to the breadboard. As you see, breadboard is pretty early on. It's, I don't want to say easy, but it's beginning of huge effort. And this arrow should be in the exponential kind of logarithmic scale, where going down increases exponentially costs, time, complexity of the operation. Additionally to this integrated breadboard, we also had ambitious goal set by our customer to go in most of the tests to go in processor in the loop. So our processor, our flight representative processor of 250 megahertz. And skipping all the building of the platform, all the interesting things for some of you, for sure. We ending up in the Mars yard. Our facilities here in Stevenage, 30 by 15 meters of sandbox, specifically built for navigation on for not researching but validating visual navigation. And then some of those aspects, some of those shakedowns aspects need to be done outdoors. So we do not have better choice than going to the parking lot and testing things like run through GPS system, or if our cameras are properly tuned and filtered for the external use. And now we're coming closer to the actual drive, to the actual field trials. Only when we exercise everything in Mars yard and in the parking lot, we can go there. And this is Quarry nearby in Milton Keynes in UK. That was out of convenience and some of the COVID restrictions back in the days. It is basically 150 meters by 30 of sandy terrain of different slopes and undulations, and we've added features by us, negative like craters and trenches, positive like multiple big or smaller rocks. Everything done to fulfill the use cases here. Follow path, human directed drive, you can imagine what's that. Autonav, so autonomous navigation, so full stack of processing and execution of autonomous navigation. Then COPSA, what's called, so it's a follow path with safety assessment, which is basically lightweight mode of autonomous navigation for easy terrains. Long traverse that I will be talking about on the next slide. Lander mockup approach, so basically to see if our solution can come to something shiny that is close to the rover and do not fail. And depot traverse, so precision navigation, precision traverse to the pickup locations, and a lot of stretch goals. Obviously, field trials cannot happen without fun. So we've seen rain. Wow, September in UK, right? We've seen wind moving our sample tubes or taking off the SRL mockup, so the lander mockup actually flew away during the test, and some invasion of the wildlife. And 300-meter traverse. As I said, I mean, back in the days of these field trials, that was really ambitious goal. It is still on the edge of what is achievable with those systems. And it was successful. I mean, we are proud of it. We like, well, basically first time we achieved such an ambitious goal in the development outdoors. You can see all the traverse, 115 navigation stops, 300+ meters of drive within 4 hours of moving, 4 hours plus of moving. For this level of system validation, it is something impressive, I promise you. I know it doesn't look so. And then what about multi-agent, because the workshop is about multi-agent systems. So in the context of big critical missions, it's not yet there. And it won't be there for, let's say, few years. But we can start considering that as a kind of coordination between scientific rover, fetch rover arm. All of those systems are typically separately controlled from the operator point of view, from the ground, with some tasks. So we can consider this cooperation as kind of heterogeneous multi-robot system. Obviously, for our research work, we happen to be involved in some multi-robot systems research related to scouting the terrain in front of the big scientific rover for faster traverses. You can find the information online or ask me. And quick conclusions. It seems that the problem should be solved a long time ago, right? I mean, well, navigation of the rover from point A to point B. And it's not. I mean, we presented for the first time for such a high level of validation that is actually achievable those days in the flight representative hardware. Then keep it stupid simple. That's the rule. That's the basic rule of establishing any requirements for space missions. You need to go from something really simple to complicated, not other way around. Full stack product development, that's something that we can be proud of as a team. And two major gaps that I can kind of advertise in front of the researchers is ultra efficient scalable solution for simple tasks. So I'm talking here about something that can be run on big computer running your solutions typically, and the same time on the 100 megahertz processor, and I get results with less quality, maybe with longer time, but it will work. That is something I didn't see I've seen, but it's really hard and it's really rare. And resources constraint algorithms. So algorithms where I can define how much resources I have for it to get particular result. I think those are pretty ambitious goals, and I heard already that this is not the research topic anymore, but I think it is. I mean, I haven't seen solutions yet. And thank you very much.
Thank you, Piotr, for a nice presentation. Questions for Piotr? Yes.
Eddie Tunstall, Motor Space Systems. I sense a sort of melancholy in your presentation regarding the experience and the cancellation. I just wanted to make a comment if I could. I've been doing this sort of thing for over 30 years now, and there are many, many instances of a project that you've done a lot of preparation for, not actually going the long haul and somehow getting canceled or defunded or something
Sure.
like that. So don't feel too bad. All the things that you and your team have done have been very valuable, and another opportunity will come.
Sure, thank you very much for that. Well, I didn't mention that. I think it's on a slide that actually even if the SFR was canceled, the ESA really wisely put this effort back to kind of technology development plan. So we still, to the end of this year, we still continue developing those technology, and we have another field trials coming in this September to kind of close them in the highest possible readiness level. So they kind of consciously aware, and we are consciously aware that this is building overall portfolio of the European market for any future missions. So we kind of positive that we will be able to use it one day.
Any other questions for Piotr?
So yeah, very interesting work. Just one question. So you talked about the fill test in Milton Keynes. So what was is there anything like everything went according to your plan, or there are surprises or something where you thought, okay, this is a new challenge which we didn't think about it in terms of hardware and computation?
Gotcha. Well, I will be boring to say that personally, I've been super surprised that many things went according to the plan. And I've been on many field trials before, on many tests before, and it was 2 weeks of field trials and basically 10 first days of struggle to get anything working. In this case, I mean, well, I think thanks for the approach we taken with the customer, thanks for kind of transformation we done to our team to work in more agile ways, etc. We delivered really well, and the things that were not going well were actually, I mean, the things that we could say we didn't finish were only in far third level of stretch goals, you know, where we thought, oh, maybe we can try this or that. So 300-meter traverse, for example, was kind of stretch goal that we never, I mean, we didn't have in our plan before field trial started. So actually, we've been super proud of the experience. Yeah.
Thank you. Any other last question? Short one, Piotr.
Yeah, one of your conclusions was basically, or your hints for future work was basically to go to very low complexity algorithms. So I would like to actually ask the contrary. How do you see perspective for more powerful hardware like processors, FPGAs, and so on? For instance, what we've seen on Ingenuity, so not like going from a 200 to a 300 megahertz radiation hardened processor, but to something like completely new.
Sure. I got this question twice already today. So if you want details or more opinions, we can talk on the corridor. But first thing I want to mention, and that actually refers to your presentation, it is not only about the algorithms or solutions that are suitable for those low computational platforms. I'm also happy to hear kind of validated ready solutions that can represent completely different approach of neuromorphic approach or bio-inspired in general. Those are really interesting ways forward. But the effort of validating it, I mean, we as an industry typically work in the ways that we need to bring it slowly, we need to bring it step by step to the picture. Why? Because of the criticality of the missions. If we talk about, you know, like a effort of sending small rover to the moon, or maybe CubeSat or whatever, something like that, you know, you have a lot of things to play. You know, I specifically build this presentation only on our kind of critical experiences, because this is something that defines our strengths in Europe and across the world, actually. But coming back to your question, the effort of bringing something stronger, I mean, there are few ways how engineers can navigate through the context of those critical missions, or maybe of the market, let's say, as a space industry. And those could be, for example, defining your problem as a payload. There are some concepts in the research or in the companies where we do not focus to bring autonomy as a kind of core critical aspect of the system, but as a payload on the separate computer that could be, you know, this could be, for example, like, I don't know, automotive processor, free automotive processors, you know, going parallel and in redundancy and trying to juggle the work. The problem with all of that all those systems are proven those days in low Earth orbit. If you hear about sending such a things to space, it's typically in low Earth orbit. I mean, sending something to moon increases dramatically the complexity and kind of risk of the radiation mitigation, of the thermal aspects, etc., etc. And this is where things are going, you know, in the two opposite directions. Like, I mean, the space systems that could be built and critical space systems for big missions that need to work. But there are ways, and I mean, it's not like our company is not ambitious to bring something new. You know, we really dream about, you know, bringing the next level, like 100 more. But we also have reality to meet the requirements and to fulfill the mission. So it's not always possible.
Yeah, thank you, Piotr. And on behalf of the co-organizers, various committee members across the room, I'd like to also thank Airbus for being a silver sponsor for the
It's
workshop.
fine. Thank you very much
Really,
for
really
inviting
appreciate
us.
that. So please help join me thanking Piotr for his talk. Thanks.
Thanks.
The next speaker is Alexander Detman from Yardstick Robotics.